Okay, so if there is no question, then let's start or let's resume chapter 7 where we left last time. We were discussing the IT conditional blocks and we were discussing the syntax of it. So the syntax will look like this. You will write I, then T. So IT is representing if then block. Then X, Y, Z will be the conditions or flags represent which instruction, which upcoming instruction will be the part of if clause, and which upcoming instruction will be the part of else clause. If you want to, if this X will represent the the second next possible instruction, Y will represent the third next possible instruction, and Z will represent the fourth next possible instruction. And these flags may assign a value T or E. If you will assign it with either T, then it means that possible line which is represented by X flag will be a part of if clause, or if it will be equal to E, then in that case, that particular line which is represented by X, Y, or Z, that will be the part of else clause. In the IT instruction block, the very first instruction will be the part of if clause. So very first instruction will be represented by this particular T. You may say that IT stands for if then block, but this T is also representing that the first possible instruction will always be the part of if clause. So the first instruction must be the part of if instruction. Then the first conditional instruction after the IT execution must be a part of true clause or if clause. And all other conditional codes will be assigned from second possible instruction to fourth possible instruction. So the maximum possible instruction that can be written inside one IT block, that is a maximum that is of 4. So if you are using the conditional statements with your IT instructions, then those conditions will be assigned as a two-letter suffix with your opcode. So whenever you will write an IT block, the conditions or the statements or instructions that you will write, and those will be the part of IT either if or else clause. They will be assigned the specific conditions. For example, EQ stands for if it is equal. CC stands for if carry is clear. So these type of suffix will be added with the opcode, and those will be called the conditional codes. And if you look at the So this is the execution flow of the IT block. If the condition test, which is the base condition written just after IT condition, so if the conditional test of the conditional instruction in IT block fails, then the instruction will not execute, will not write any value in the destination register, will not affect any of the flag, and will not generate any exception. If the base condition written with the IT block is going to be true, then in that case, even if you have fetched it through a pipeline architecture, that instruction has been fetched, that instruction may get decoded as well, but even then you will not execute it, you will not write any value to its destination register, you will not change the flags, and that instruction cannot generate any exception because the conditional check written with the IT condition or IT instruction is has been falsified. This is the simple type of IT block. In this IT block, we are comparing R0 by R1. So whatever the contents of R0 register are, those contents will be compared with R1 and the flags will get updated. Once the flags will get updated, you will write IT. IT stands for if then clause, then two T's with it. Two T's means the first condition will be the part of if clause, second condition will also be a part of if clause, third condition will also be a part of if clause. There is no else in it. So this is the simple if clause which has three different conditions with it. And the conditional base condition is LT. LT stands for less than. So if your R0 is less than R1, it means my if condition is true. Only if the if condition is true, my next three lines will be executed. Otherwise, if this condition is false, even if you will fetch these lines will not get executed. And what these lines are doing just a dummy assignments like R0 plus R1. It is doing R0 plus R1, storing the result in R2. Then it is multiplying R2 by R1 and showing the result in R3 and then shifting it right in that direction by 1 times. So these are just the dummy type of arithmetic assignments just to give you an idea how the IT block works. The IT first T will stands for the first condition. The first condition will always be the part of true clause. The next possible X, Y, and Z flags may represent if or else clause. If you want an instruction to be a part of if clause, you will write T with it. If you want any instruction within your else clause, in that case, you will write E with it. And all the instructions that you will write with E subscript, those will be given a conditional suffix, which will be exactly opposite than that of base condition. For example, let's look at this particular example. In this particular example, we are comparing once again register with R1 register. So you are comparing R0's content with R1's content and you are updating the flags. Once the flags will get updated, now you have applied an IT block. In this particular IT block, now the first condition, which is represented by first T just after the I, this T is representing that the first possible condition will be the part of if clause. The next possible if the same if clause. This E is representing else clause. So if the base condition is false, then else clause will be executed, and else conditions are conditions line 3 and line 4. So line 3 and line 4 are the part of my else block. First two lines are the part of my if block, and the conditional base check is less than. So if R0 is less than R1, in that case, my if condition will be true. If the if condition is true, in that case, my first two lines will be executed. And if if this condition is false, then in that case, it is understood that GE condition will be true. This is less than. GE stands for greater or equal to. So if less than is false, it means either R1 is greater than R0 is greater than R1, or these are exactly the same variables. So it means my first condition get falsified, then my else clause will be executed, and my else clause will execute the last three lines. So last three lines will be the part of else clause, and it is being declared by these double E. And these two T's are representing that my first two lines right after the IT block will be the part of if clause. So these two instructions will be the part of if condition. These two instructions will be the part of my else block. So this is how the IT block is written, with the conditional suffix and with the T or E combinations, which are telling the compiler, or which are telling the processor, that which condition or which instruction will be the part of if clause and which condition will be the part of else clause.
सर ये कंडीशनल सफिक्सेस साथ के देने स्टेटमेंट्स के जरूरी है, क्योंकि ये तो
जी,
ऊपर से
ये
ही पता
जरूरी
लग
है।
रहा है कि
ये नहीं जरूरी है, क्योंकि जब आपने आईटी ब्लॉक एग्जीक्यूट करना ना, तो आपकी जो कंडीशंस हैं, अगर ये पाइपलाइन वर्जन चल रहा है आपके आर्किटेक्चर में, तो ये कंडीशंस आपको ऐड करनी पड़ेंगी ताकि प्रोसेसर को दोबारा से पता लग जाए एएलयू को कि ये कंडीशन एग्जीक्यूट करनी है कि नहीं करनी। तो ये उसके फॉर्मेट का पार्ट है।
सर सिमिलरली एक मिनट जरा स्लाइड पीछे करिएगा सर। सिमिलरली जिस तरह ये था कि आई डबल टी मतलब जो हमारी पहली दो हैं वो ट्रू की हैं और अगली दो हैं वो एल्स का पार्ट है। सर अगर हमें चारों एल्स करनी होती तो फिर हम सारे ईज डालते।
चारों एल्स नहीं हो सकती, क्योंकि फर्स्ट में जब आप आईटी लिखते हैं तो फर्स्ट कंडीशन हमेशा इफ का पार्ट होनी चाहिए।
एक है मतलब एक
अगर
एक
आपकी
इफ होनी चाहिए और
अगर
तीन
आपके
कम से कम
सारे
else
एल्स है ना, हाँ, अगर सारे एल्स पॉसिबल नहीं।
ठीक है सर। तो सर फिर अगर हमें तीन एल्स भी डालने होते तो फिर हम आई टी ट्रिपल ई डालते।
ई ट्रिपल ई डालते तो उस केस में तीन एल्स क्लॉज का पार्ट बन जाएंगे, फर्स्ट कंडीशन आपकी या फर्स्ट लाइन आपकी इफ का पार्ट रहेगी।
और सर एक
क्योंकि
और
अकेला एल्स पॉसिबल नहीं है सी कोड में।
सर एक और बात सर, हम इसका जिस तरह अभी फोर्थ इंस्ट्रक्शन है मेरी ASR GE, सर अगर मैं इसकी जगह पर भी एक और नया आईटी ब्लॉक यूज करना चाहता तो वो पॉसिबल है?
नहीं, आप नेस्टेड आईटी ब्लॉक यूज नहीं कर सकते। नेस्टेड आईटी ब्लॉक के बजाय आप एक आईटी ब्लॉक एग्जीक्यूट करेंगे, उसके बाद नेक्स्ट आईटी ब्लॉक स्टार्ट करेंगे। क्योंकि जब आप आईटी ब्लॉक में होते हैं ना, तो आपका प्रोग्राम स्टेटस रजिस्टर में एक फ्लैग है आईटी नाम का, अपडेट हुआ होता है, और उसमें आपको एक एक्स्ट्रा एक्सेस मिली होती है इन इंस्ट्रक्शन को एग्जीक्यूट करने के लिए।
ठीक है सर।
Okay, let's look at the next example. In this example, you have written a C code, let's suppose, and if this C code is, if x is less than 0, x is negative, then in that case, you will assign y equals minus x. So absolute value of x will be assigned to y. Otherwise, if x is positive, then in that case, x is assigned to y. So it's a just absolute value calculator. So absolute value of x, that whatever the sign is, that will be assigned to variable y. So if you want to translate this particular code onto your assembly notations, then you may also use the branch conditions as well. But now we will translate this particular code in assembly using IT statement. So in IT statement, the first line will be the comparison line. In the very first line, you will compare R0. Let's suppose X is saved in R0. So R0 has a value of X variable. So X is compared with 0. You are comparing R0 by 0. And the if condition was less than, if R0 or X is less than 0. So in IT block, these are just two lines. One line is for the if clause, one line is for the else clause. So you will write I, T, and E. So I, T, E stands for the first condition will be the first line. Right after this line will be the part of if clause, and the next line will be the part of else clause. And the base condition is LT. So LT stands for less than. If R0 is less than 0, this is that line. My if condition will, if the if condition is true, then in that case, next possible line will be executed. And the next possible line is RSB. RSB stands for reversed subtraction. Reversed subtraction means I will perform 0 minus R0. So 0 minus R0 means I am computing minus X. So that minus X will be stored in R3. Let's suppose R3 is a register reserved for variable Y. So variable Y's value will get updated to 0 minus R0. This is reverse subtraction. And if the if condition was not true, then in that case, my else clause will be executed. And in the else clause, I am just moving the value of R0 in R3 directly without any sign conversion. So in that case, my y equals x will be executed. In the if condition, my y equals minus x will be executed. And the base condition was LT. So this is the way in which there is no label called, there is no branch called, there is no condition checked, condition is checked with the branch, and there was no branch penalty in it. So that is the most optimized version of this if else clause onto directly to the assembly. Now, although IT is a highly optimized version of branching, but it has some serious restrictions. What are those restrictions? A branch or any instruction that modifies the program counter must either be outside an IT block or must be last instruction inside the IT block. You cannot write down a branch statement in your IT block at the first line or second line or at the third line. So it is recommended to never use a branch statement within the IT block, because if the IT block is in execution, then all four instructions must be at the consecutive addresses, and those four instructions will be executed based on the IT flags. So you cannot apply any branch condition within the IT block. If you want to apply a branch, then that branch condition must be the last line of IT block, so that all four instructions will remain a part of the same or the consecutive addresses scheme. The next restriction is do not branch to any instruction inside an IT block. You cannot assign any inside instruction of IT block to a label. You cannot assign a label to any IT blocks instruction. You cannot create a branch to it, because that will create an error. So you cannot create a branch to any instruction that is a part of IT block. You cannot assign it a label. Then the third restriction is all conditional instructions except the conditional branch must be inside an IT block. All of the conditional instructions, they must be the part of IT block. You cannot write in conditional instruction independently. Those conditional instructions must be a part of some IT block. Then conditional branch instructions can either be outside or inside an IT block. The conditional instruction, there is no restriction on conditional branch instructions, but I am in the previous there was a condition, there was a restriction on conditional instructions. These are the conditional branch instructions. Conditional branch instructions can be used anywhere in your code. And the conditional branch instruction have a larger branch range when they are used inside an IT block. Whereas in the start of the chapter, we discussed that if you are inside an IT block, then in that case, your branch instructions offset value will have a larger range than that of the previous range. So if you are inside IT block, your branch will also have a privilege to have an offset from -2 KB to +2 KB, even if you are 16-bit encoded instructions. Similarly, if you are inside IT block and you are executing 32-bit encoding scheme, then in that case, your branch instruction will have an offset ranges from -16 MB to +16 MB of IT block. Then in the architecture level, your branch will have a larger offset value when you are calling that branch inside the IT block. But the restriction is that conditional branch statement must be a part of the last possible IT block statement. So that conditional branch can be called inside IT block, but in that case, that should be the part of that should be the last line of IT block, and that will have a larger offset value residing to it, assigned to it. Using the IT conditional statement, you can execute the nested conditions as well. And what are those nested conditions? If R0 is larger than R1, this is the C code, then you are adding another if clause. If R1 is larger than R2, then another nested if clause, which is R2 is larger than R3, then in that case, assign R4 equals to this value. So this type of nested if condition can be executed using a single IT block. And what is this IT block? You are comparing R0 by R1. So compare R0 by R1. The very first check, the main check of the if clause, the conditional check is larger than. So you will write greater than. So greater than, and all of the coming 3 instructions will be the part of my main if clause. So this is my main if clause else in it. So all 3 possible instructions will be the part of my if clause. Now, if I go to the main if clause, in this main if clause, there is another if condition. So I have to update the flags again. So in that case, as you can see over here, I am subtracting R1 and R3 together. So R1 and R3, the difference of R1 and R3 will be computed. If R1 will be larger than R2, then in that case, my result will be positive and my flags will get updated based on that check. So R1 and R2 will be subtracted from each other, and they will also assign the results in R5, which is just a dummy assignment. We do not need the result of it, but since we are in IT block, we have to check that R1 is larger than R2 or not. So in that case, I will subtract R1 by R2, assign the updated value in R5, which is a dummy assignment, but I will also update the flags as well. So the flags of the program status register will get updated. Now, when I will execute the next line, the next condition, which is this GT, it will be checked based on the most updated values of flag. So based on the most updated values of flag, which is if R1 is larger than R2 or not, in that case, my GT condition will be checked. This GT will be different than that GT. In that case, the most updated versions of flags will be used to apply the condition whether this is true or not. If this will be true, in that case, this line will be executed. Otherwise, this line will not get executed. Once again, the third line is my another if condition. In this if condition, I am subtracting R2 by R3. So R2 minus R3 will be computed. Result will be stored in R5. Once again, this is a dummy assignment, but during the assignment, your flags will get updated once again. So if the flags are getting updated, it means the previous values of flag are helping this GT to apply a decision whether to execute this instruction or not. If this instruction will be executed, then those flags will get updated once again based on this condition. And if this condition is also true, then this GT statement, this GT flag will once again be applying the check on the latest values of flags. So the latest values of flags were updated on this particular if check. If this if check was true, then in that case you will assign the value to the R4 register. So this is the way you may apply the nested if else conditions onto a single IT block in a more efficient way.
सर इसमें जो सी वाली इफ कंडीशन है, इसमें जो फिर कंडीशन है ये सेम ही होनी चाहिए, मतलब ग्रेटर देन ही हो सकती है ना? अगर ये दूसरे में if R1 इक्वल R2 होता तो फिर इसको इंप्लीमेंट कर सकते
हाँ, नहीं फिर इसको इंप्लीमेंट नहीं कर सकते, फिर इसको ब्रांचिंग के थ्रू ही करना पड़ना था।
सही है, ठीक है।
So, अगर ये आईटी ब्लॉक ना होता, इस आईटी ब्लॉक से हमने यही काम 5 लाइंस में किया। अगर ये आईटी ब्लॉक ना होता तो आप अंदाजा लगा सकते हैं कि अगर सिंपल ब्रांचिंग करनी पड़ती तो उसके लिए 2 लाइंस तो कंपैरिजन और ब्रांच कॉल करने में, उसके बाद नेक्स्ट 2 लाइंस फिर से कंपैरिजन ब्रांच कॉल करने में, तो आपके पास सीरीज ऑफ लाइंस आ जाती जिसमें जंपिंग वगैरह हो रही होती हर बार। तो इससे ब्रांचिंग के केस में इसको इंप्लीमेंट करना और मुश्किल हो जाता। बट यूजिंग आईटी ब्लॉक you have executed that particular nested if condition in just 5 lines. So let's look at the last possible example of this chapter. In this example, we are computing the GCD of 2 numbers. So this is an algorithm. You may test this algorithm if it is working or not. Just give any A or B values to this function and apply a check whether it is calculating the GCD correctly or not. So it's a GCD computing calculator. In this particular function, you are calling a while loop, and this while loop will keep on iterating itself unless these 2 numbers will become equal to each other. So if they are not equal, then it will keep on iterating itself. And during the iteration, it is doing an if else check. The if condition is if first number is larger than that of second number, then in that case I will subtract the first 2 and I will assign the updated value to the first variable. And if B is larger than A, then in that case I will subtract B and A and I will assign the value I will update the value in the second variable. And at the end of this whole while loop iterations, A will have my GCD value, which is the largest number which is dividing both of these 2 numbers. So this algorithm is very efficient algorithm to compute the GCD of any 2 numbers, sorry. Now the goal is to convert this particular C code onto the equivalent assembly code using minimum possible instructions. So if you want to execute or if you want to convert this code into minimum instruction, then you have to use IT block. So you will use IT block. There is one while loop in it. There is one if else clause in it. And there is a subroutine calling which is called GCD. So if you will write down the particular code onto your pages, then we can switch to the next slide to see what is the converted assembly code of this particular function. Now this is the converted code. GCD is the name of my label. I will compare R0 by R1. Let's suppose A variable is stored in R0 and B variable is stored in R1. So I am comparing R0 by R1, and if they are equal, branch equal. If they are equal, then it means this while loop condition is false. If this while loop condition is false, it simply means I will just skip this iteration and I will return. So to return to the main or return to any other particular line, you will simply call a branch if equal to stop. So this is my stop label. So I will just ignore these instructions, instantly jump to stop, and this stop will keep on executing the program where it was left. So branch equal to stop. If this condition is false, it means my while loop condition is true. So if the while loop condition is true, then in that I am inside this while body. So I am inside this loop body now. Within this loop body, there is an if condition, there is an else condition. To perform the else condition or the if condition, what is being written over here is this is BLT. BLT stands for branch if R0 is less than R1. So if R0 is less than R1, it means my A is less than B. A is less than B means I will switch to the else clause. So if A is less than B, I will go to less. Less will execute my else clause. If this condition is also false, then it means my if condition is true. And if the if condition is true, then in that case, I will perform the if condition clause. I will go back to GCD again. Even if I was in else clause, in that case also, I will perform the else condition. I will perform the else execution, and I will go back to GCD again. And this loop will keep on iterating itself unless this condition gets satisfied. Once this condition will get satisfied, I will terminate the loop here and I will go to stop instantly. So this is the GCD implementation using the conditional branch instructions. So this was the implementation using the branching, which we have discussed in the first part of this chapter. Now let's complete or let's translate this code onto the equivalent assembly code using IT instructions. So this is the another version of GCD implementation in assembly using IT statements. Within this IT statements, this is my GCD. So GCD is the name of the label or name of subroutine, you may say. You are comparing R0 by R1. Once again, you will compare R0 by R1. You will start the IT block because this IT block was a part of my while body. Within this IT block, the condition is greater than. If R0 is greater than R1, so R0 is larger than R1, which is my A and B respectively. So if A is larger than B, then in that case, my if condition will be true. If it is less or equal to B, then in that case, my else condition will be true. So I will perform the if condition execution if this base check is correct. And I will perform the else clause execution if my base check gets falsified. And the last line is branch. If R0 is not equal to R1, in that case, I have to go back to GCD again. So the last line of this code will be to create a branch to GCD once again if they are not equal to each other. So if they are not equal to each other, then my while condition is still true. And if it is still true, then in that case, I will go back to loop again. So this is the way of converting that particular C code onto the equivalent assembly code using IT statements. So as you can see, the IT statement works through only 1, 2, 3, 4, and 5 lines. So you have performed or you have translated that code in just 5 lines. While in the previous version, you were using 1, 2, 3, 4, 5, 6, 7 lines. So this is the least efficient solution. This is the most efficient conversion. So if this particular execution is if you pick this particular translation into the assembly code, or one student will translate the assembly code into this version, in that case, if you will run this algorithm on to, let's suppose R0 is 1 and R2 is 2, then in that case, the conditional branched version of that assembly code will execute GCD value in 13 clock cycles, while the IT block execute in 12 cycles. Similarly, if you will run this algorithm, same algorithm, with A is equal to 10 and B is equal to 24, then in that case, conditional branch will take 45 clock cycles, while IT block will only take 40 clock cycles. So this is a performance efficiency of IT block, that even if you are using the smallest possible values of A and B, even in that case, IT block execution is still efficient than that of conditional branch execution. And that's it for chapter number 7. We will not compare the table branch instructions for this particular course. So these are just slides to be ignored. Any questions so far?
मतलब हमारा सिलेबस खत्म है मिड के लिए.
जी, मिड टर्म के लिए आपका सिलेबस बस यहाँ तक ही है. बट सिंस आपके मिड टर्म जो है वो अनसिमेट्रिकली प्लान्ड है. अनसिमेट्रिक प्लानिंग इसलिए क्योंकि आपके मिड टर्म से पहले 10 वीक्स हैं और मिड टर्म के बाद आई गेस सिर्फ 6 वीक्स हैं. तो इन दैट केस वी विल स्टार्ट द पोस्ट मिड सिलेबस राइट नाउ एज वेल. सो हम लोग पोस्ट मिड सिलेबस के भी 2 चैप्टर्स मिड टर्म से पहले कवर करेंगे.
सर 2 ज्यादा
सिंस
नहीं
अनसिमेट्रिक है ना, इसीलिए तो पोस्ट मिड के 2 वीक्स के लेक्चर्स पहले रखने हैं मिड टर्म से, ऑल दो ये सिलेबस का पार्ट नहीं होंगे, लेकिन इसके बारे में एक क्विज जो है वो राइट आफ्टर योर मिड टर्म हो जाएगा आपका। तो इनिशियल प्लानिंग यही है कि 10 वीक्स के हिसाब से आपके मिड टर्म का पैडिंग की जाएगी, सिंस
सर
आपके
अगर
भी 2
उसका
वीक्स रहते हैं ना।
सर अगर उसका क्विज फॉरेन मिड्स के बाद ही हो जाएगा तो हमें तो वो साथ साथ करना पड़ेगा पूरा काम, तो सर वो
नहीं,
काम बढ़ा
दरमियान में कुछ टाइम दे देंगे आपको, 1 वीक का या 2 वीक्स का टाइम दे देंगे, क्योंकि आपका अभी तक कोई क्विज प्लान नहीं ना हुआ, तो आपके जितने भी क्विज होंगे वो सारे पोस्ट मिड एरा में ही होंगे अगर आप ऑन कैंपस आते हैं। अभी तो स्टेट ऑफ अनसर्टेनिटी है थोड़ी सी,
जी सर
तो
अभी
अगर
तो
आप पोस्ट मिड आते हैं तो आपकी सारी असेसमेंट थ्योरी की जो है वो तब होंगी, क्योंकि हमने कोई क्विज प्लान नहीं किया ऑनलाइन ऑनलाइन सेशंस में, तो आपके वो
ओके
सारे
सर
क्विज कंसेक्यूटिवली होते रहेंगे फिर। Anyways, the last or the post mid part of your of this course is based on the TIVA board. So all the next possible chapters, starting from chapter 8 till your till the chapter 12 of this textbook, you will, ये किसी का माइक कौन है यहाँ पर? So starting from chapter 8 till chapter number 12, we will keep on discussing the embedded boards, and we will keep on discussing their peripherals and their configurations. So the chapter 8 is a very fundamentals or basic chapter in which we will discuss only the GPIOs. The GPIO stands for general purpose input and output pins. So in this particular chapter, we are going to discuss how a single pin of a microcontroller can be programmed for different purposes, and for those purposes how the configuration steps will change, what are the registers to be accessed, and how the registers will get updated based on the configuration steps of GPIOs. So this chapter will be based on just a basic introduction of GPIOs. Then we will discuss what are the features of TM4C123 GPIO. That is a board that you are going to use in your lab sessions as well. So for lab sessions, we will discuss what are the performance or performance features of that particular board's GPIOs. Then we will discuss the configuration steps, how a microcontroller pin can get configured whether as input or output, whether as an analog pin or as a digital pin. So these are the those configuration steps will be discussed, how a single pin can be configured. If you can configure a single pin, whether as an input or as an output, then in that case you may configure a complete port as well, because the whole settings will get multiplied if you want to configure 10 pins or 13 pins or even 15 pins. So in that case, we will configure a single pin of microcontroller. Then we will try to configure multiple pins. We will try to multiplex them together, and we will discuss a few examples in which we will be configuring the LED. We will be blinking the LED, which will be connected to a single pin. We will be using a switch to get an input to configure a particular pin as an input device, or we will configure the 7-segment LEDs that will be required 7 GPIOs for the data bits and 4 GPIOs for their controlling anodes. So in that case, we will configure 11 different GPIOs in parallel. And also we will discuss how to configure a keypad as well. That keypad is basically a module that will be giving you an input to the microcontroller. So we will configure multiple lines as an input, and we will discuss how those lines can give you a authentic keypad value using some interfacing. And in the last part of the chapter, we will discuss LCD interfacing. So LCD interfacing, 7-segment interfacing that you have initially covered in your DSD course as well. You know how to multiplex some different anodes, how to give data to different anodes. So 7-segment interfacing, the keypad interfacing, LED interfacing, and switching. These will be the examples of this chapter. But from the start, we will discuss what are the GPIOs. We will discuss what are the special features inside the TM4C GPIOs, and how can you configure a single pin onto a TM4C GPIO. So starting from the start, first the GPIO. GPIO stands for a general purpose input output port. So a GPIO is a physical pin inside a microcontroller that can be configured by some software to become either digital pin or digital output pin or even analog input pin as well. So this is not written over here, but once we will start the ADC section, the analog to digital converter section, then we will discuss how to configure a single pin as a digital, analog input as well. So you may configure a single pin by software by either as a digital input or digital output or analog input. The voltage levels on the pin configured as a output allows the microcontroller to exert an on-off control to the device connected to that pin. If that pin has an LED connected to it, if you want to turn it on, you will give it a high logic or high voltage, and if you want to turn off that, then in that case you will put a low logic or low voltage on that pin. So using a pin as an output means you are controlling some output device, you are controlling its functionality. And if you are using a GPIO as an input, then if the GPIO will be configured as an input pin, in that case, software will read the external digital signals into the program. You will read the data from that pin. If the data is 0, then in that case, signal is providing you a 0. The input device that is connected to sort of embedded software, that is giving you a 0. Or if that pin is giving you 1, it means that external digital signal or digital sensor is giving you a logic high value. So the software will read the external digital signals value into the program to get the current state of the connected device. Whatever sensor or whatever input device that you have connected at that particular pin, you can get the current status of that particular sensor just by reading that line, by reading that pin. So that pin can be configured as either input or as an output. If you are using it as an output, then in that case you are basically controlling the output device. And if you are configuring that pin as an input, then in that case you have just attached a sensor to it, and sensor is controlling that pin. You are just reading the value of that pin. Now, this concept of pull up and pull down, you have already, I think, covered this concept in your electronics course as well. If you will, these pins are actually the switches. So the switches are being manipulated as transistors. So those transistors may have a pull up resistance attached to it at the collector side, or pull down resistance attached to it at the emitter side. So if you have a pull up or pull down configuration, then in that case, the pull up resistor pulls the GPIO pin up to the logic high value. The pull up configuration, आप लोग सबको पता है ना pull up configuration कैसी होती है, कैसी होती है? अगर मेरे पास यहाँ कोई डायग्राम हो. This is a pull up configuration. आप assume करें कि यहाँ एक ट्रांजिस्टर लगा हुआ है. For this transistor at the drain side or at the collector side, you have attached a pull up resistor. So in that case, if this NMOS transistor will be at 0, which means short circuited, then output will be 0 and all the voltage will drop at this resistance. And if it is open circuited, it is 1, then in that case for open circuited version, no current will flow through it. There will be no voltage drop at this pull up resistor, and all the voltage will come across the NMOS transistor. In that case, my GPIO pin will give you a 1. So the pull up configuration function is basically, if you will turn off this switch, you will short circuit it. There will be no voltage across it. All the voltage will be dropped across pull up resistor. Then in that case, this logic value will be 0. And if this is open circuited, then in that case, no current will flow through it. No voltage will drop across this resistor. In that case, all the voltage will be dropped across this open circuited NMOS transistor, and GPIO pin will give you a logic high. If you use a pull down configuration will be inverted. In that case, a resistor will be attached with the ground and the emitter side. So for that purpose, your output will be across the resistor. Whatever the voltage across the resistor is, that will decide the logic value of that pin. So that is pull down configuration. So this type of configuration is called pull up configuration. So pull up configuration, the pull up resistor pulls the GPIO pin up to the logic high value. Each GPIO, if you are using a GPIO with some external sensors or with some external devices, each of these GPIO will have a limited current sourcing. Current sourcing means if you are configuring a pin as an output, then you can apply a very minute amount of current to the output device. You cannot attach a motor directly. एक मोटर अगर 50 वॉट की है या 100 वॉट की है, तो if that motor is demanding 8 ampere or 10 ampere current, a single GPIO cannot provide that current. So a GPIO has a very limited current sourcing ability. In the case of output, you can attach a maximum of 1 LED or 2 LEDs with the current with a single GPIO, and that will be more than enough to drive it. And a very limited syncing capability as well. You cannot attach a sensor that is providing 1 ampere current to a pin. That pin will get burned out. So a GPIO pin has a very limited current sourcing ability and a very limiting current sinking ability. Those sourcing limits and sinking limits varies from port to port or pin to pin. So we will discuss in the data sheet of that microcontroller that a few pins may have a larger current sourcing ability, that is, let's suppose of the range 16 milliampere, and a few of them has a very limited current sourcing ability, which are, let's suppose, 2 milliampere. So that is a particular range of a GPIO current sourcing and current sinking ability. And the last thing is, most of the GPIO pins within the microcontroller can be configured for an alternate hardware functionality as well. There are multiple alternate hardware functions that are available in the microcontroller as well. So apart from its general purpose GPIO pin configuration, you may configure a single pin as an alternate functionality as well. That alternate functionality can be that GPIO pin can be alternatively configured as a UART receiver, or that can be configured as a UART transmitter, or that can behave as a SD card reader, or similarly that pin can behave as a timer signal. So a timer can be configured to a pin. Similarly, an interrupt can be configured to a pin. Similarly, any other peripheral device like I2C, SPI, master slave protocol, those type of configurations can also be done on a single pin. For that purpose, you have an additional function or additional registers attached to each port, and that register will decide whether the GPIO will behave as a GPIO as its default value or as an alternate functionality. So if you are using an alternate functionality, then the alternate functionality's configuration has to be configured at a given time. So GPIO pin can either behave as a GPIO, or it can behave as a specific functionality or alternate functionality module as well. But only one of those alternate functions can be configured at a given time. A GPIO pin, a single GPIO pin, can be attached to multiple hardware modules, like a UART receiver can be attached to it, a timer can be attached to it, an SPI receiver can be attached to it, an I2C master can be attached to it, but only one alternate functionality can be configured at a given time. A single pin cannot behave as a timer, as a UART, as a I2C receiver at the same time. So only one alternate functionality can be configured at a given time. This is the block diagram, a simple block diagram of a GPIO pin. GPIO pin is readable as well as writable. There is some flip-flop attached to it. There is some bus attached to it. The processor will give the data to the bus. If you want to read something, then read flag will get updated, and whatever that GPIO's pins value will be, that will come out from that buffer, and that will, excuse me. I'm sorry. As I was discussing that bus will give you some commands. Bus will give you the data bus will give you the data. The control bus will give you the command lines. If the processor want to read something from, then read signal, read flag will get updated. Whatever the current state of GPIO pin will be, that will be passed through that buffer, that will pass through that flip flop, and the data bus will get updated to the current value of GPIO status. And if the processor wants to write something onto the pin, then in that case, this data that is coming from the bus will be passed through this flip flop from the input side. This write flag will get updated based on the enabling of the this G flip flop. The data will be passed through that flip flop, will pass through that buffer, and the GPIO pin will get updated. So the lower line is representing the output functionality. the upper line is representing the input functionality of a pin. So how the data will be driven when the pin will be behaving as an input, and this line is representing how the data will be transferred when this pin is behaving as an output. So it's a simple illustration of a GPIO implementation with your data bus and with your control signals. So this read, direction, and write are the control signals that will be passed from processor to the control line. And this is the same configuration with the pull-up configuration as well. You have attached an external pull-up resistor to it just to make sure the logics will remain between 1 and 0. There will be no open drain logic, or there will be no obsolete logic if GPIO pin is floating in the free space. This is a more compact version of a GPIO configuration. In this compact version, there are a few additional modules as well. This module is once again a flip-flop that will be triggered using the read signal. This is Schmitt trigger. This Schmitt trigger is once again is being used just as a logic divider. This is once again a flip-flop. This is drive logic. A control signal will be coming from it, data signal will be coming from it, and based on the current status and based on the control configuration, a specific drive logic will be set. This is a slew rate. Do you know what is slew rate?
Yes, sir.
The slew rate is basically a slope of the voltage rise or voltage fall with respect to time. So if you have a very fast clock coming from the bus side that has a maximum value, let's suppose 70 megahertz, and you want to switch a single pin at 70 megahertz starting from 0 volts directly to 5 volts or 3.3 volts, then the slope from 0 to 3 volts with that minimum number of minimum time interval of 2 clock cycles, that will decide the slew rate. So if the slew rate is larger than that of the maximum capacity of these transistors, then in that case the voltage will not be able to rise from 0 to maximum value or maximum to 0 value in that limited clock cycle time. So this slew rate will be controlled using the drive logic, and that slew rate will be toggling that particular pin onto some particular clock signal. So whatever the clock frequency will be, if you want to toggle that pin will start toggling from that position to the maximum position, and these will be the configuration. These will be the additional hardware blocks that will be controlling the drive logic, slew rate control. Now comes the GPIO configurations or GPIO features of TM4C controller. The TM4C controller that you are going to use in your lab sessions, in your on-campus lab sessions, it has a processor which has a clock frequency up to 80 megahertz. So 80 megahertz is a maximum clock frequency that can be given to a processor with a floating point unit. It also has an FPU in it. Although we got FPU and we haven't discussed the FPU's configuration in architecture part as well, but still, this is the Cortex M4 type of architecture, and M4 architecture also contains an FPU as well. So it has 80 megahertz clock frequency with an embedded FPU in it. It has a SysTick timer. Now, what is this SysTick timer? We will discuss this SysTick timer in chapter number 10 when we will start the timers. So SysTick is a 24-bit clear on write decrementing timer, which can be used as a time-based generation due to its flexible control. Now, what are these things? These things will get covered when we start the chapter number 10. And this microcontroller provides a JTAG and SWD serial wire debug based debugging interface to the programming and debugging purposes. So it is configured with Keil, and it provides a JTAG and SWD debugger interface. So you can call a debugger onto that microcontroller directly as well. So if you want to load a code, you can debug that code before loading that code directly onto the flash of microcontroller. These are some enhanced features of it as well. The microcontroller has an NVIC installed in it, the nested vectored interrupt controller. The NVIC can prioritize and handle the interrupts in handler mode. It will once the interrupt will arrive, it will start handling it, and the NVIC will be evoked in the handler mode, and it can prioritize those interrupts as well. For example, once the interrupt has arrived, it will have a limited priority. If another interrupt has arrived once you are in the exception or in the handler of that interrupt, it will prioritize those interrupts as well. So NVIC can prioritize the interrupts. A collection of 7 system exceptions and 65 peripheral interrupts are supported by TM4C. So TM4C can support 65 different peripheral interrupts. It can support 7 different exceptions. And it can support 8 different priority levels, starting from priority 0 to priority 7. How these priority levels are set and how they are supported, this thing will be covered in chapter number 9. So chapter 9 will be based on interrupts. Chapter 10 will be based on timers. So we will discuss the timers configurations in chapter 10. We will discuss the NVIC configurations in chapter number 9. So as for just for the sake of record, you can say you have 8 different priority levels starting from 0 to 7, and you can prioritize your interrupts based on the priority levels of each exception and each interrupt. As far as the pin is concerned, the microcontroller TM4C123, the microcontroller that you are going to use in your lab, has a 64 pin package of it. If I have the diagram of it, this is the diagram of the TIVA board. This is the diagram. It has a total of 64 pins attached, half at the right side, half at the left side, at the right side. Each pin has been given a name. For example, this particular pin has a name PF2. This particular pin at the right side has a name ground. Similarly, the left pin has a name PF3. The right pin has a name PB2. So each pin has been given a unique name. Similarly, over here as well, you can say this pin is called PB5. This pin will behave as a ground. Similarly, this is PB0, this is PD0. So each pin has been given a name that is written on the TIVA board. So you have a flexibility of using 64 different pins. Among those 64 pins, only 43 pins can behave as GPIO. So among those 64, you have flexibility of using 43 pins as GPIO, and these 43 pins have been divided into 6 different ports. So these 43 pins have been divided into 6 different ports, and each port has a name starting from port A to port F. So when I will go to the diagram again, this PF3 stands for, this is port F third pin. So PF stands for port F, PB stands for port B, PC stands for port C. So each of the GPIO has been assigned to a specific port. So starting from port A to port F, port A to port D, the 4 ports have 8 different pins in it. So starting from PA0, then PA1, PA2, PA3 till PA7. So PA will have 8 pins, PB will have its own 8 pins, PC will also have 8, and PD will also have 8 pins, starting from 0 to 7. Port E is a short port which has 6 pins in it, and port F has only 5 pins in it. So this is the classification of these 43 pins onto different ports. Now 43 can behave as GPIO, but the total was 64. So among those 64 pins, some of the pins also have the special peripheral functionality attached to it. So a few of the GPIOs and few of the other remaining pins may have a specific or special peripheral functionality attached to it as well, that can be configured in the GPIO configurations. If you want to configure a pin as an alternate functionality, that special peripheral device must be multiplexed with that GPIO pin. Then 13 pins are used for power supply and ground. A few of them are ground, a few of them are VDD, which is providing 3.3 volts. 4 pins are reserved for the connecting external clock source and the connectivity, and rest of the pins are reset pins, wake up pins, hibernation pins, and external battery connection pins. So these are the packaging details of the TM4C microcontroller. There are 64 pins. The more concerning part of 43 GPIOs, 13 are VDD and grounds, 4 are reserved for clock purposes, and rest of them are just for the reset, wake up, hibernation, etc. So if you want to configure a GPIO pin will have a few capabilities. What are those capabilities? Each GPIO pin may have an internal pull-up or pull-down resistor. You may configure it as a pull-up configurable pin, or you may configure as pull-down configuration pin. So it has an internally connected a switch connected with either pull-up or pull-down resistor. Then the current sourcing capability. Each pin has a limited current sourcing capability. For example, 2 milliampere, 4 milliampere, a few of them has 8 milliampere as well. But there are 4 different pins in the microcontroller that can sync up to 18 milliampere as well. So up to 4 GPIO pins when configured as inputs can sync 18 milliamperes. That is a maximum current syncing or current sourcing capability of any GPIO pin. The slew rate control capability is provided for 8 milliampere output drive. Each port pin can also be configured as open drain. Now, what is this open drain? We'll be discussing in a little while. And some of the port pins are capable of tolerating 5 volts as well. Also, the microcontroller works at 3.3 volts, but some of the ports, some of the pins can also tolerate 5 volts as well. But it doesn't mean कि आप project में 5 volts पे attach करते रहेंगे. 5 volt कुछ देर के लिए वो attach करेगी, sustain करेगी, शायद sustain कर भी ले कुछ देर के लिए, but still it will get heat up. This is the minimum connectivity portal. If you are controlling or if you are designing your own microcontroller, then these 4 things has to be attached. जी.
सर अभी जो आपने पहले बात किया है उस हिसाब से हम सिर्फ 3.3 वोल्ट वाले सेंसर यूज कर सकते हैं.
जी 3.3 वोल्ट वाले सेंसर ही सिर्फ यूज कर सकते हैं.
5
जो
वोल्ट
इसके
वाला नहीं
अंदर
यूज हो सकता.
नहीं 5 वोल्ट वाला यूज नहीं हो सकता. वो जो आपका आर्डिनो है ना, आर्डिनो इस मामले में 5 वोल्ट सपोर्ट करता है, लेकिन जो आर्डिनो के अलावा बाकी जितने भी कंट्रोलर्स हैं वो सब 3.3 वोल्ट सपोर्टेड है. इनके एडीसीज भी 3.3 वोल्ट सपोर्टेड है.
ओके सर, और एक और बात थी कि हमें इसके लिए ऑप्टो कपलर यूज करने पड़ेंगे.
जी ऑप्टो कपलर यूज करने पड़ेंगे क्योंकि ये पिन की सिंकिंग और सोर्सिंग एबिलिटी बड़ी थोड़ी सी है. तो अगर बैक करंट आ गया ना, बैक ईएमएफ की वजह से मोटर के साथ, तो वो बैक करंट आपके कंट्रोलर को डैमेज कर देगा. तो ऑप्टो कपलर बेसिकली वो आपको एक फ्लेक्सिबिलिटी देते हैं, एक पार्टीशन दे देते हैं कि आपकी कंट्रोलर साइड आपकी पावर साइड से बिल्कुल सेपरेट हो जाती है. ग्राउंड सेपरेट कर देती हैं दोनों का. कंट्रोलर का ग्राउंड सेपरेट होता है, पावर ग्राउंड सेपरेट होता है. तो वो ऑप्टो कपलर साथ यूज करने पड़ेंगे. So the minimum wiring of a microcontroller, if you are designing your own microcontroller, you starting from a chip of the microprocessor, then it requires for proper functionality, it requires a minimum of 4 things in it. And those 4 things are, it should have its own DC power supply, it should have a clock source, it should have a reset pin, it should have a debugger interface. So these 4 things are necessary for designing a microcontroller. If you have only a microprocessor chip, and if you want to build that chip onto some microcontroller, then these 4 hardware connections are necessary for it. But that is just a redundant detail. Let's switch to the main or more important details. That is just a summary of it. It has 43 configurable GPIOs. It has 80 megahertz maximum clock frequency. It can hibernate. It has 8 different UARTs with it. It has 4 different SPIs. It has 4 different I2Cs. It has 2 CAN buses and 1 USB device interface. So these are the special or general features of TM4C microcontroller. We will be configuring the UART as well. We will be using SPIs as well. You may use I2C and CAN bus in your FYPs as well. And there is one USB drive device attached to it. You have multiple timers. So you have 32-bit timers, you have 64-bit timers, you have watchdog timers, you have ADCs attached to it, which two different ADCs channels which are attached built in the microcontroller that has a maximum resolution of 12 bits. You have 2 analog comparators. You have QE, you have EEPROM of 2 KB on chip EEPROM with your microcontroller that will be storing all the variables and all the codes that you will write on TIVA board. This is its memory map. It has a fixed memory map of 4 GB addresses. So 4 giga addresses can be generated with the flash memory of it. 256 KB on-chip flash is reserved for the code memory. So the code memory has a maximum capacity of 256 KB. Whatever code you will write in your TIVA C board, that should have maximum capacity of 256 KB. You cannot give the code of larger capacity to its flash board. So 256 is the maximum capacity in which variables or data lines or instructions can be assigned to it. And that address ranges from all zeros to 3 all Fs. So this is a limited capacity of 256 KBs in the code memory segment. RAM has only the capacity of 32 KB. You can assign variables in the RAM section or data section only of the maximum capacity of 32 KB. अब 32 KB से ज़्यादा capacity के variables define नहीं कर सकते. And that has the starting address starting from 2 all zeros to 20007FFF. This is the data range or address. Sorry, this is the address range of 32 KB on-chip RAM memory. And the address range assigned to the peripheral is allotted to different configurations, control, status, and data registers. So the addresses to the peripherals that is not constant, that can be assigned using different configurations, control, and different status registers. Next comes the configuration steps. If you want to configure a single microcontroller pin as your GPIO, then you have to do these four different things. Each configuration steps required setting or clearing a bit field. Each register, whichever register is assigned to that particular port, each register will have its own register map. So by reading that register map, you may get the information that which bit is representing which type of controller, which type of control. So if there is a register in which each bit is representing one pin, so by setting that pin, you may say that I have attached a pin as an output. Similarly, if by resetting that pin, you may say I have attached that signal as an input. So each configuration steps basically require setting or clearing a specific bit field in one or more register. If I will say I will set a bit means it is equal to 1. And if I will say I am clearing a bit means I am setting it equal to 0. And if I want to configure a simple GPIO, I have to configure first of all its clock, I have to configure its bus, I have to configure its data control. Data control means whether it will behave as an input or output. I have to configure its mode. Mode means it's digital or analog. And I have to control its padding. So these four different type of control configurations has to be done if you want to configure a single pin. First, you have to configure the clock. You have to configure the data control. You have to configure the mode control and pad control. These are the four basic things that require to be done if you want to configure a single pin onto a microcontroller. The very first control is a clock configuration. For the clock, बल्कि आपका लेक्चर स्टार्ट हो जाएगा, हम लोग कॉन्फ़िगरेशंस जो वो नेक्स्ट लेक्चर से स्टार्ट करेंगे. We will start the configurations and examples from the next lecture. अभी के लिए आप वो लेक्चर ले सकते हैं अपना.
Excuse me sir.
जी
सर वो आज की लैब में सर क्या करना हमने?